So the agenda of today's is to basically find out what are the SRE strategies for these training workloads. We have model training, large scale model training happening, and this how big are these models? These models are 1 trillion parameters big. So when we are training these models, what kind of SRE challenges you will face and how do we deal with that? It will be very high level, so we'll go right from the basics, right? I think the agenda here is the first thing is scale challenge. So as we know, there is 1 trillion parameters, so the scale is very high. And then when scale is high, what are the challenges there and how do we deal with that? Then we'll talk about a little bit about SRE limitations. We have traditional SRE, which goes on, which is about online traffic and batch jobs, map reduce jobs and Spark jobs. But this machine learning workload is a little bit different. So we'll talk about what are the limitations there and maybe opportunities too. And then next is distributed architecture. What is the training architecture that we use to train these big, large models? We'll talk about failure modes, then some monitoring recovery and key takeaways. Okay. So let's get started. The first thing is scale challenge, right? So as we know, these models are really big. So the cost of training these models are super high, right? And then we're talking about GPU nodes. How many GPU nodes are required to train these models? So for 1 trillion parameters, if we talk about how much data, it is about 4 terabytes of data to store these parameters. So just we are saying, okay, one parameter takes about 32 bits. So then if you compute it, about 4 terabytes. Then for each parameter, we have something called gradient that we need to compute, right? So that is another 4 terabytes. And then we have an optimizer state that you need to maintain. It will be depending upon what kind of optimizer you're using. You're talking about another 20 to 30 terabytes. So you're talking about, 30 to 40 terabytes of storage just to say that, okay, my model is here. This is the state of my model, right? So to maintain that state, you need memory, right? And you have to put all this into GPU nodes. So if one GPU got say 80 GB of memory, then we're talking about these many data basically to store on GPU. So we're talking about thousands. How many thousands? About 5,000, 3,000 to 5,000 nodes. And these all nodes has to be working at the same time. They have to be up. At least most of them have to be up at the same time for this model to train, right? So it's very different from the traditional world of Spark MapReduce jobs that, okay, if you have 10 nodes, then also it works. If you have 20 nodes, then also it works, right? So it's not like that. So this is a little bit different in that case that they have to be coordinated. And the last thing is runtime. How long does this take to train these models? So we're talking about 2 months. So basically, how do we compute these 2 months? For many months. Basically, we're saying 1 trillion parameters, and then you have 1 trillion parameters and they are layered. So these parameters are basically layered. These are like neural network layers. And then you start from here and you go back there. So you're talking about those many flops, those many floating point operations we are doing just to go and get an iteration. So to go from here and come back here, because when you are coming back, you are tuning all those parameters back. So going is a forward pass and coming back is backward pass. So in that, you tune those parameters. When you're tuning those parameters, we are talking about 2 exaflops. So exa means 10 to the power 18. So basically that many floating point operations are required just to do one set of tuning, right? And we have to do this for, based on how big is the model is, we have to do it hundreds, thousands of times. So with that, it comes around 10 to the power 24 or something like that. Those many flops, order of magnitude flops we need. Right. A cluster, like a GPU node cluster of 5,000, 3,000 to 5,000 cluster will produce about 1 trillion flops. So with all these computations, it will come around 2 months to train these models, right? Assuming everything goes well. But if everything doesn't go well, we'll stop it, restart it, and it will just additional time. Okay, so that is the scale problem. So what's different from traditional SRE here? We talk about the first one, state complexity. Because the state is big, so to maintain a state, you need 40 terabytes of data. So that is a big thing, which is different. The second is communication overhead. We talk about all reduced operations. What is this all reduced operations? So all reduced basically means that you have a tensor. Tensor is nothing but array of numbers. And then this array of numbers is so big that you're not able to put that into one node. So you have to break it down and put it in multiple nodes. And then you do all those compute on all those nodes. And then you have got the updated values for all those entries, right? And then you have to synchronize this back. So you'll say, okay, now I have to get back the numbers into everything not distributed. So you have to basically synchronize all these nodes where you distributed your tensor. So that basically is the all reduce operation helps us do that. This is provided by NVIDIA. Some libraries are available. There are NCCL libraries that helps us do that. But to do this operation continuously, 100,000 plus times. So that basically is a communication overhead that comes in. So as you know that we are basically talking through networks. So if there is one congestion, then it will just spirals across. So that's the biggest problem in the communication overhead. The next one is recovery time impact. In our traditional SRE, if you're traditional online services or others, basically you just restart the server. It might help to solve the issue, not always, but might solve the issue. But in this case, in model training, if it is going on for months and you say, okay, something is not working, let me restart it. Oh God, everything is, you have to start it right from the beginning, right? So we have checkpointing available, that cost is much higher. If a single node failure basically will make the cost of a training higher and the time to get it trained also becomes longer. Moving on. So we talked about SRE challenges. Let's talk about what is this stack we're talking about. Where is it really happening, right? So there are 3 layers. So on the top layer, let's talk about the framework layer. So we'll go to framework, then communication, and then there is, of course, the infra layer. Right? The framework layer, basically, we have many players in the framework layer, but I'm from Meta, so that's why PyTorch wins. But generally PyTorch is not because I'm from Meta, but PyTorch is the kind of winner there. That library is mostly used. And on top of PyTorch, we have some more frameworks like Megatron, which is from NVIDIA, and we have DeepSpeed from Microsoft. And these basically framework layers are basically helping us train the model, right? Then after that, these are basically just helping you on the application framework layer, right? So the next layer is communication layer. Communication protocols like NCCL and InfiniBand. These NCCL libraries basically help you to coordinate between all these nodes. And then basically gives us these operations like all reduce and all those operations we talked about. So that is given by NCCL, that is the library. And InfiniBand is the mechanism which is used to communicate between 2 nodes. So that is your communication channel between 2 cluster nodes. When I say cluster nodes, one node can have about 8 GPUs together. And then similarly, you have multiple nodes. And then between them, you have this InfiniBand. But inside a cluster node, which have 8 GPUs, then you can have, in that communication layer, it will be different. You can use NVLink or something, which is much faster. So that is the communication layer. The next is infrastructure layer. Then in the infrastructure layer, you can have Kubernetes orchestration or something, which is an interface, which will actually talk to your bare metal servers and everything. So this is mostly the training stack we're looking at. Now think about what are the failure modes in this distributed AI training. One of the biggest problem here is like silent performance degradation. So what happens is that your training is going on fine, and then suddenly it starts slowing down. Why it is slowing down? Because there are multiple things that can happen. Your bandwidth is being used too much, because we are talking about this all reduce operation has to happen. In every time you have basically this big tensor, which is distributed. So every time you are trying to compute the gradients and updating this, then the all reduce operation has to happen. And when it is happening for 2 months, definitely there will be some time something will blow up. And when the bandwidth is so basically, this bandwidth also means that so the training is happening on GPU, and then you are feeding data from CPUs, because your data, the training data is not living on the GPUs, right? GPU is only maintaining the state of the model. So the data, when you are pushing in that from the ingester, we are pushing in to the GPU, that time you can also see a lot of congestions. So the second one is complex network congestion cascades. So if there is one congestion somewhere, because everything has to work in unison, so you will have cascading failures there. And of course, there is some GPU thermal throttling events that can happen. And people say that I haven't seen a GPU, no, not a data center, but then people say that it is hot, that it can actually physically really melt if the cooling is not good. Okay, so that is performance degradation. Then another one is the critical gradient synchronization failures. So there is another problem that all reduce operation, you can't just keep on waiting for all reduce happen. So there will be a lot of timeouts. If there's a timeout, then basically it's like you have to restart it again. So that is another problem. Timeouts are happening, then basically your training is not going well. Then intermittent communication ring breaks. This is again the same thing, that you have a ring because you are doing, when you're doing all reduce, you basically provide chunks. So for example, we are all our nodes, GPU nodes. So I have a chunk, I will give it to you, you will pass it to him. And then similarly, we have basically everybody will have one chunk where I have basically sum of all the chunks. And then on that chunk, basically we'll pass it again. So we'll form a ring, and that will basically so it's optimization of the all reduce operation. So if something one breaks, then basically everybody of us will have the incorrect value basically. So if that ring breaks, will also again all reduce operation will stall. That means training is also stalling, or it is basically slow. So those are the failure modes. So how do we resolve this? So if there is a failure, and then you have to restart it. So to restart it, basically we need a checkpoint from where we'll restart. So checkpointing is very critical. But as I said, the checkpointing means basically what checkpoint really means is that the whole state of training until now, you have to put it in somewhere, right? So we're talking about 40 terabytes, you have to put it somewhere, right? And then if you try to just create checkpoint all the time, we're talking about 40% of your computer will go into checkpointing, right? So that's a big problem. So frequency of checkpointing is very critical. Obviously, we want checkpoint for every iteration so that we have really strong failure recovery handling. But the problem is that it has performance overhead. We'll try to make sure that frequency is tuned. Then the next thing is storage architecture. How do you really checkpoint these things? How do you really do this? So the architecture of checkpointing is that for every node, instead of we basically collecting the state values from each of the GPU node, every node basically can store it locally, its state locally. And then in an async way, we'll try to pull all those together. So checkpointing is going on simultaneously and training is going on simultaneously, right? That's all great. Checkpointing also going on, training also going on. What happens whenever everything goes simultaneously? Nothing is going well, right? Something is failing. So what is going on here is, so how do you verify that whatever you capture in the checkpoint is actually correct? So for that, we need a validation pipeline. So validation pipeline, what it does, it automatically checks or rigorously keeps on checking whatever checkpoint we built is actually good. And whenever things actually fail, we'll be able to load it and actually run it, right? So that is the validation pipeline. So there's a lot going on here. We have checksums, we have make sure that we can load it, we can basically run it. So that is another async process where we'll make sure that checkpoint is good. Okay. Okay, so we got our distributed running stack, we got our checkpoint, so everything is running. Now we want to see that whether our training is actually happening. Because just updating some parameter pointing is not the end goal, right? The end goal is basically a machine learning, is that our training is that we have to measure the loss curve. We have to make sure that the loss curve is basically going to or converging, right? So to do that, we have to observe what's going on here. So comprehensive observability is required. So what are you observing? So traditional infrastructure metrics, we all know that we have been in the SRE conference, we have heard about it, all infrastructure metrics we are covering. But apart from that, what new metrics here are? The new metrics is model-centric metrics. So how the model is performing, I talk about the loss curve. So loss was earlier in the beginning, it will be high, but slowly loss will keep on going down. But if loss is going down, after suddenly loss goes up for some reason, that means your training is not getting performed really well, and then everything is basically you have to shut down. And then, so basically that's why we have to make sure that we keep on observing that how the loss curve is going. If the loss curve is not going well, our training is not working fine. So another problem we have is that, okay, so we talked about 5,000 nodes running in parallel, and then we are training the model. What happens generally, if your job is running for 2 months, some other high priority job will come in and kick you out. So in that case, what do you do? So that means basically, so the main problem here, what happens is that we have situations wherein our job has to be stalled in between because some high priority job came in, because CEO wants Llama model needs to be trained first, right? So in those cases, we have to make sure that dynamically we are able to our configuration so that we can stop the job in between obviously with a checkpoint, and then we can restart it later. And also it can be tuned that, okay, right now I have 5,000 servers, so I can go use 5,000 servers, but if I have only 3,000, I can also still right? So those are the things which we need to be looking at and to observe it. Let's look about what are those multidimensional monitoring observability metrics that we are basically monitoring. So we talked about this model metrics. So we have loss curves, we have gradients that are going on. Of course, learning rates also we need to find out. And if we find any divergence, as we talked about, if the pattern is not converging, then in that case, we need to basically take action. The next one is communication metric. We talked about a little bit that the bandwidth is not used. Then if a bandwidth is not getting used, that means there is some problem. You have booked all your GPUs, but data is not going. That means basically your training is not progressing, right? So that's why bandwidth also you have to monitor. And then your all reduced latency will give you if it's timeout happening. If it's retrying all reduce a lot of times, that means basically your training is very slow. And next, message queue depths. So basically, whenever this all reduce operation happening, it is basically queuing up messages for every node. So if the depth is increasing, that means basically you are getting blocked. So those kind of communication metrics we need to basically keep an eye on. The last one is resource utilization. So GPU utilization metrics is a really, it can write a book on it. There is so many different things on GPU utilization. There's GPU utilization, there is SM utilization, there is like too many different utilization metrics that can be tracked. But here we're talking about two things. GPU's memory, of course, GPU's usage also we need to look at. Then the CPU utilization basically because the data is always loaded using CPU into the GPU. So we have to ensure that CPU utilization is not too high. If CPU utilization is too high, that means basically what happens is your data loading is when the data is required to load on GPU, you don't have the CPU to actually load. So similarly, we have storage, IO throughputs. We need to monitor all these. Okay, moving on. Next one is, okay, so we are monitoring and we found something, and then what do we do after that? So the first thing is we have autonomous systems that are in place that we detect that, okay, node failures and communication failures and performance degradations. If any of these happens, basically we have to detect that. And then the next thing is impact assessment. So there are two different kind of impact assessments we can do. The one is that, okay, the loss curve is not diverging a lot. Then the impact is basically the training is not going well. Training is not going well. So basically we have to maybe stop the training. If some node failure happening, we have to isolate the nodes. And basically whatever impact, we need to assess that impact. And then the recovery execution, we have different kind of recovery executions that can happen. We can have automated recovery, basically. Automated recovery in the sense that one automated recovery is that just stop it and basically restart it later with some tuned parameters. So what are the parameters are we tuning here? Basically, there are different kind of parameters we can tune in a machine learning model training. So one of the thing is what is the parallelism we can do. So I was talking about that this tensor, we are breaking the tensor and we're putting it in multiple nodes, right? So you can say, okay, what is the amount of parallelism you want? So those can be tuned. Then you can say, okay, I have a machine learning model which have say 100 layers. So instead of breaking the tensor, I will basically put the layers, the first two layers in one machine, second two layers in the second machine, third two layers, like that. So I can basically divide in the layers. So that is another tuning parameter we can tune. So basically we can stop the job and say, okay, we have less nodes because one node got down, or basically there are dynamic resourcing crunch. So we have to basically use some less nodes. So you can say, okay, these many nodes, and this is my batching style. Now this is my parameters that I can tune. The data parallelism or model parallelism or the tensor parallelism, all those knobs I can tune. After I tune it, then we can automatically start the training again. So if you have automated recovery, then basically you don't have to, because you have a big cluster and a lot of jobs are running. So you have to make sure that you tune it automatically and restart the job instead of human intervention there. So moving on, I think this is basically was capacity planning for AI workloads. This is for bigger companies that, okay, what is the capacity need that you need for later? So the first is GPU and computer memory. This keeps on increasing. So you need to make sure that if you can get more from NVIDIA and if you have the money, you buy it. Similarly, network throughput. So AI workloads generally keeps on increasing and it needs more and more network. Again, if you have money, then buy it. Storage IO performance, if you can forecast it, you can get that. And then the last thing is power and cooling infrastructure, because these are power hungry. These all jobs are power hungry, right? We're talking about for every one run, we're talking about a lot of power and about 10 to 12 million of dollars for one training job, right? So these are the capacities needed for this training. I'll skip this thing because it is basically energy aware resourcing. Okay, so this one is incident response. So what if there is incident, basically how do you tackle that? There is nothing new here. It's the same thing. You detect it, you assess the what is the basically impact of that. You do try to do some mitigation, and then after that you do some analysis to figure out. This is the standard stuff that we do in all kind of incident management. Reliability engineering, again, I think chaos engineering is the very pretty standard. Everybody does that. The next thing is I would like to touch upon synthetic load testing and validating performance. So we're talking about these jobs which are running for 2 months. So how do you basically validate things and basically make sure that before you basically embark on this journey of training these models, your setup is good, right? So to do that, we basically have to do some validation. So how do you do that? Basically, we can stress. So I talked about these parameters that we have. So we have batch size parameter, you have learning rate, you have basically tensor parallelism. So those knobs we can basically try to tune and run a very small job, 1 day, maybe 1 week, and basically validate all that. So when you run that job, you have to make sure that the communication stress, how much communication stress is happening. If your parallelism is not set correctly, like tensor parallelism and model parallelism, pipeline parallelism is not set correctly, then you'll have a lot of communication stress. So that will monitor. The second basically will monitor is gradient synchronization. So how is your gradient synchronizing upon? Basically, you have to make sure that gradient is synchronized across these nodes. So how is that happening? The third one is the checkpoint recovery. Your checkpoints are getting created, but actually you can, if anything goes wrong, you can actually do recovery from that. The checkpoint really will actually loads the state correctly and recover from whatever state it was. So this is very critical before you embark on this journey of testing or training. Moving on, so these are some operational metrics. Sorry. So this is some operational metrics. One of the operational metrics is sustained training uptime. We need basically exceptional reliability in here because, as we say, if there is some node failure, then you come back to the last checkpoint and you basically lose a lot of time and money, right? So that's why this is sustained training uptime is a big metric for operational excellence. Then minimal recovery overhead. Whenever there is something happens and you are trying to recovery, how much overhead is there? The last thing is, I think this is very normal, that what is your response time? Moving on. So I think we're on the last slide. So basically, a key takeaways we have is multi-dimensional monitoring, not only monitoring, but we have to make sure that model level monitoring is also in place. Convergence of model is very important. That is the first thing. Resilient degradation, we have to basically make sure that we have everything in place so that we can recover from errors. And of course, there is automated recovery, which helps us do that. Okay, that's all. Thank you very much.